Okay, let's start our sharing. And welcome everybody to come to my sharing. And before I start this sharing, I want to do a quick survey. Have you heard TiKV before? Raise your hand. Okay, yes. Have you heard TiDB before? Okay, great. Have you attended last year's My Talk? Raise your hand. Oh, old friend. Okay, great. Yeah, and today's topic is scaling TiKV with S3 as the backbone, Supercharge cloud-native SQL database with object storage. Yeah. And this is a little bit about me, Jinpeng. And I'm working for TiDB right now. And I'm the maintainer of TiKV, contributor of RocksDB, and have a few years of experience with search engine, natural language processing, and a recommendation system. But for the past nearly 11 years, I was working in scalable data platform and the database area. And for the past 9 years and 5 months, literally, I built TiKV and TiDB from scratch with other engineers. And this is my GitHub and my tech blog. Yeah, today's sharing will cover 3 major topics. The first topic is about the new challenges for databases in the age of AI. I know AI is a very hot topic right now. And the second topic is about object storage. It's becoming the de facto of distributed file system on the cloud. And the third topic is about how we leverage object storage in our system. Okay, let's come to the first part. It's new challenges for databases in the age of AI. Right now, after the large language model, and I can imagine that everything between, the interface between human and the computer is becoming the natural language. And from the database area or data platform area, there is a domain that is text to SQL, because SQL is an interface for like a data scientists and the data engineers to send requests or send instructions to data platform or database. And right now, because of the large language model and the natural language instructions, or natural language become the new interface between human and the computer. So when we come to the database or data platform area, because the natural language is is a language that is ambiguous. And it's not like a compute language or SQL. It's unambiguous. So when people send some natural language instructions to the AI agent or to your systems, and the AI agent need to know what you want to do with the data. And because of the natural language, it's ambiguous. So there is some research or some effort that to make the text to SQL the accuracy is higher and higher. But eventually, it's really hard. And I know the right number is around 80% accuracy for the text to SQL. And so right now, recently, there is another trying to overcome this challenge. Is how about let the AI agent to generate multiple different SQLs, and this will be covers the most case of the natural language is ambiguous. And just run these different SQLs parallelly. and get the multiple result to the human, and let the human to make choice which one is exactly you want. And this is a fantastic, I believe, practical rules. It works. But when we come to the backend database or data platform, this will be increased concurrency or the workload of the background database and your data platform. So this is introduced a little bit like I call it volatility. And sometimes the generated SQL query is not optimal. And the second challenge we can see is the AI agent are generating vast volume of data at unprecedented speed. There are two numbers. The first number is 57%. This is a recent report that the new generated data, 57% of them are generated by AI agent. It's not generated by human. And this number is becoming more and more larger. And the second number is 45% of compound annual growth rate. This is the enterprise adopting the AI system speed. Its growth I believe is a high number. And how we can store such large amount of volume of data cost effectively in terms of like economic your business value must be like higher or way larger than the cost you spend on store or keeping these data. And most of you have used like ChatGPT, and I use it daily. And sometimes you can, I use ChatGPT as an example of AI agent. We have multiple conversations with AI agent every day, and sometimes because AI agent has already extended our consciousness, and we extended our memories, extended our knowledges. But sometimes you want to review or retrieve the topic or the conversations you have had, like 1 month ago with your AI agent, to recall your memory or to recall your knowledge. And how we can retrieve the context, the context of the conversations you have had with the AI agent in seconds, in milliseconds, not in tens of seconds. And you can see the modern AI applications or modern applications expect databases to have better elasticity and efficiency. Elasticity is equal to the volatility of the AI workload come to data platform or databases. And the efficiency is equal to the challenging of the generating data is coming larger and larger. And let's move to the next part. This is the architecture of TiKV and TiDB. When we come to about scenarios, and we do have some challenges. Because this system is built 10 years ago, and we refer to the Google Spanner paper, and we adopted the disaggregated compute and the storage architecture. So in this architecture, we can scale the compute layer and the storage layer respectively. But when we come to the scenario I just mentioned, it's not cost effective enough. Because in this architecture, we store all the data in our storage node. And if we think about the cloud deployment, we usually use the cloud disk, like EBS, and to achieve the durability of the data. But when we come to the massive data volume scenarios, this is not cost efficient. And from the elasticity perspective, the compute layer is scale fast because it's a stateless. But when you come to the storage layer, the data is on each TiKV node. When we want to scale out or scale in the storage layer, it will involve moving data between these nodes. So you need to think about how this data moving can impact your latency, how this data moving can eat the resource, compete the resource with your online traffics. And the second topic is about object storage. Object storage is becoming the de facto of distributed file system on cloud. And because of the great elasticity and the great cost efficiency of object storage, it is used everywhere nearly, like analytical databases and the backup and the AI training data. And but the latency is acceptable for those systems. But when we come to scalable OLTP database like TiKV and TiDB, the latency is not acceptable. So the question is, can OLTP databases leverage object storage without compromising latency? Yeah, this has become a question for us a few years ago. And the answer is yes. And the key is just involve object storage with background operations, background read, background write. Yeah, this is the principle we adopted for our new TiKV architecture. We call it object storage powered TiKV. And this is the basic architecture of new TiKV. At the most part, it's the same as the classic TiKV, except the storage engine, we integrate this storage engine with object storage like S3 and the GCS. And so we keep the rough log, which we store the rough log in the cloud disk with multiple copies. So make sure every modification is persistent. And we flash a chunk of data to the persistent remote object storage to make sure the data is persistent. And after doing that, we can truncate the transaction log or rough log in our cloud disk. So let's analyze the read and the write paths to see what we have achieved. And remember our principle, we need to just involve the S3 with the background operations. So from the write perspective, we separate the foreground write and the background write. When the request is coming, and first we need to write it to our rough engine, which is a storage engine to store the rough log. You can think about it, this is a transaction log or redo log in other database system. And this is attached with a cloud disk. And the storage layer, we have the instant store. And after the rough log has been replicated to multiple TiKV nodes, and we can apply the change to the storage engine part. And at this step, we just apply the change to the memory table of our storage engine, which is really very fast. It's like just modify the buffer pool in MySQL or Aura. And then response back to the client or to TiDB. And after a while, there must be accumulated a batch of modifications in the mem table. And in order to keep the memory usage of the system is consistent, and we need to flash the change, this batch of change to the remote object storage. And after doing this, we can truncate the memory and the rough log. And from the read perspective, the read, at first, it will read the mem table, which is, contains the latest modifications. And then read from the instant store, which is, has the SS tables. And if the case is there is a large amount of data and most of data is code, we will introduce a feature named tiered storage. So the code data will just store on the object storage. And in this case, if the read query didn't find the result in the first step and the second step, and we will try to locate the SS table files on remote storage, and then bring them to the instant store and to serve this read request. And this is only happens when the tier storage is enabled for the code data scenario. And let's see some numbers. And this is a cluster that with around 50 terabyte data, and there is 27 TiKV, and each of them has 1.8 terabytes of data. And the QPS is around, the write QPS is around 1/10,000 per second. This is 2 PC, pre-write and commit. So actually it's 200 some number thousands per second write to TiKV. And there are 20K get queries. Yeah, because this is a online system for our customers, so I don't have to do the benchmark things. I just made some screenshot to share here. And we can see the P99 latency of the write is around 3.2 or 0.1 milliseconds. This is the P99. And the read is 0.2 millisecond for the get. So we even with use the S3 or object storage at the backend, we kept the consistent low latency for our system. And the second benefit or the challenge we have just mentioned is how we can make our system more elasticity. And the key for our TiKV layer, because it's a stateful storage layer system, and we need to make it scale out and scale in fast and seamless. So after introduce the remote object storage as our backend, we can quickly to pull up a new TiKV node and just pull the data from the remote object storage to the newly added TiKV node. In this way, and then definitely we need to build some raft connections, and then to catch up with the latest modifications from other TiKV nodes. And by doing this, you can see we have minimized the impact to existing storage nodes. And this will incent to speed up the scale out and the scale in process. And we can see some numbers. Still the same cluster. And last night, this customer did a scale in. And they scaled this 27 TiKV nodes cluster to 18 TiKV nodes. And the whole progress, it takes 1 hour and 1 minute. When come to the classic architecture, I can remember some numbers. It's because you need to consider, for the classic architecture, you need to consider how we can minimize the impact to existing TiKVs, to existing online traffics. So we will control the scale limit, scale speed of our system. So basically, it will come like 10 hours, even longer. So after introduce this new architecture, it's 10 times faster. And when you look at the latency, this is just slightly, for the right perspective, during the scaling, the latency is from 3.2 to 3.3 some number, millisecond for the P99. And with the QPS 135,000 per second. And from the read perspective, because there is less TiKV nodes, so the total memory is less than before. So it's around 0.2 to 0.3 millisecond because you shrink the total memory. So the cache hit ratio is lower than before. But overall, the latency is still promising. And by introduce the object storage, we have other benefits. And when we come to the volatility of the workload, and there might be some heavy queries from our database perspective. Heavy queries means there are table scans, there are do some calculations for a range of data. And if we don't use if these queries run in our regular TiKV nodes, you can think about it will eat a lot of resource, and it will compete the resource with online traffic. And so keep the low latency of your online traffic consistently is a hard challenge. But after introduce this remote object storage, we can easily pull up a new elastic read worker and to pull the data range or the bunch of data they want from the remote object storage, and then to serve this heavy read queries. And by doing this, we can isolate or we can minimize the impact to the regular online traffics. When we come to the large amount of data scenario, for example, we just mentioned the AI-generated context scenario. Also, we have some other similar scenarios like operation logs or historical orders. And this data will going up and larger and larger. But as time passes by, most of the data is become cold and rarely accessed. So in this case, we can did some statistics for different part of the data, and to judge, okay, this is going to code, and we will offload the data to the remote object store and evict it from our storage node. And this will reduce our storage cost by a lot. And there are other benefits to introduce the object storage at the backbone of our system. For example, we can use a centralized compaction service to do the data compaction or data reorganization works, and then to share the result with different raft copies. So for different copy of the data, you just doing once and share the result. And we also think about the recovery scenarios. When there is one TiKV node crash, and we can quickly add a new storage node and pull the majority of data from the remote object storage, and then to build the raft connections to catch up with the latest modifications. And in this way, we can minimize the impact on the remaining storage node. And we also can increase the recovery speed. When we come to the backup, in the classic architecture, we need to copy the data from different storage nodes. And this will also introduce some interference with online traffics. So we need to introduce some resource throttling, backup throttling mechanism to make sure the backup works, doesn't impact the online traffic's latency. And by introducing remote object storage, because the majority of data is already in the object storage, and the backup is just copy some metadata which described what access tables this table or this database contains, and then catch up with the newly modified rough log to this backup. So the majority of the work is done in the background and doesn't involve the online storage node. So this can also minimize the impact to the online traffic. Yeah, this is pretty much I want to share today, and hopefully our work can give you some input for your system, or you can just use our system to power your business. Yeah, thanks. Yes, and after this session, if you still have some questions and want to have conversations with us, yeah, can we visit our booth 451? Yeah. Any questions? Don't be shy, just raise your hand. Oh, yeah.
For your read latencies, I was just curious if those included any of the cold reads.
No, it doesn't involve the cold data. Yeah, because if it's a cold data, oh, sorry, it's distance. Yes. Yes, this doesn't involve the cold data. Yes.
I figured it couldn't.
Yeah, yes. This is for the regular. Yeah.
And
for the cold region, it varies because when we practice with S3, AWS 3, the latency is varies when you retrieve different size of the object. And it varies from 20 milliseconds. This is maybe the best case. And even there 300, even 400 milliseconds. So yeah, it's not that stable. Yeah. We still have 1 minute? Yes, okay. Sorry, I can't hear you. This is why I tell.
Okay, yeah. So my question was, how straightforward was it to like use this across different cloud object stores like S3 versus GCS? Like, did you find it easy to abstract over those different object stores, or do you have a lot of challenges in doing that?
The question, yeah. The question is how we, I mean, the S3, GCS, or Azure blobs, and what's the difference, or does the difference introduce challenges for our system? Am I understand correctly? Okay.
Yeah.
The answer is no. We have a extract layer for different object storage. And so from engineering perspective, we just need to adopt different vendors. And from our system design perspective, even you can think about even the S3 is bad, is like a 30 minutes latency. Bound-wise is 100 gigabytes per second. Compared to like a GCS or other vendors, or even yourself built in, the performance number is worse. Let's say 100 milliseconds. But it doesn't make sense, or it doesn't make difference for our system, because we just do the background jobs or background operations in our system. So we don't like depend on the latency or on the especially on the latency for the different vendors' object storage. Yes.
Thank you.
Yeah. Just let, I think the only depends on the object storage is they are minimal bound-wise. And the latency is not too bad. And yeah, the bound-wise is enough. That's all. Thank you. Time out. If you have any questions, you can just come to me, and we can have more conversations. Yeah. Thank you.